Let us consider lattice dynamics in this class. We will first consider this in the harmonic approximation and then talk about the need for considering anharmonicity. So lattice dynamics essentially means the equations necessary to describe lattice vibrations. So we will start with a simple monatomic lattice. That means only one atom per lattice site. The atoms are labeled in terms of n-1, n plus 1 and so on. The lattice constant is A. The displacements of the nth atom, n-1th atom are represented by the u's here. So I can write the force on the nth atom as some force constant C times the relative displacement between the n plus 1th atom and the nth atom, and the n-1th atom and the nth atom. So I'm just only considering near neighbor interactions. So the equation of force becomes this, and I can think of a traveling wave solution where I have q is the wave vector of the lattice wave. Xn is simply n times a. That's the position of the nth Bravais lattice point. So if I stick that inside, I get that. I get rid of common terms, and I will be able to write an expression for the frequency in terms of its wave vector q. This is called the dispersion relationship. So this relationship is plotted here. I don't need to plot this over all q values. I just need to plot it between minus pi by a and plus pi by a, because those are the only unique q value that resides within the first Brillouin zone. So if there are n lattice points, there are n q values within the first Brillouin zone, n wave vectors in the first Brillouin zone. So if for q equal to plus or minus pi by a, I can just put that inside here and show that I just get traveling waves. Instead of traveling wave solutions, the usual solution is traveling wave, but at q equal to plus or minus pi by a, I get standing wave solutions. That's just Bragg reflection. So again, you have a concept of Bragg reflection. So we have seen Bragg reflection 3 times in this course. 1 for externally applied X-rays, 2 for electronic wave functions, and now 3 for lattice waves. All of them satisfy the Bragg reflection Bragg constructive interference condition, and you basically have standing waves at plus or minus pi by a instead of traveling waves. So I can now think of a group velocity, which is the velocity of the wave, the lattice wave packet, and this is the phase velocity. So the group velocity is given by this, and it's easy to see that the group velocity becomes 0 at the zone boundary. If I just substitute there, I will be able to show it's 0. So you can also find the velocity in the long wavelength limit, that is in the q equal to 0, approximately q equal to 0 limit. You can also see what happens here, and show that you get normal sound waves, that are simple wave velocity expression, and that's just the limit when you have sound waves in the solid. When I now introduce one more atom, so I have a one-dimensional solid, and now there are 2 atoms per Bravais lattice point. So that's called a lattice with a basis of 2. So this is one Bravais lattice point. This black and white represents one Bravais lattice point. So at every Bravais lattice point, I have 2 atoms, and you have a diatomic solid. Now things change quite dramatically when I have a diatomic solid, and also I must mention that when we talk about lattice waves, please recognize for every wave vector there are 3 polarizations. You can have a longitudinal vibration, and you can have true transverse vibrations. So there are 3 polarization modes possible for every wave vector. We saw that also in previous classes. So I will now write the equation of motion for the 2 atoms, the nth atom and the n plus 1th atom, using considering just near neighbor interactions, and that will be just this. Now again, I consider traveling wave solutions of this form for the nth atom and the n plus 1th atom, and that's just written in simple matrix form, and I can put that inside the expression for the force, and get this kind of a matrix equation, and obviously this determinant should vanish to get solutions. And so if I write down the determinant, I get that expression for determinant going to 0 as that, and that gives me a nice quadratic which I can solve to get these as the roots. So now I get a dispersion relationship with two possibilities. So I have two branches. So I get a dispersion relationship which looks like this. The lower branch is called the acoustic branch, and the upper branch is called optical branch, and the frequencies lie in the infrared region, and some of the modes in the optical region can result in polarization of a solid if the two atoms are plus and minus in each Bravais lattice point. If two atoms are plus and minus, I can have polarization, a polarization wave traveling through the solid. So the electromagnetic wave, at least a part of the electromagnetic wave, can travel through the solid for the optical modes, as we shall see now. So at q equal to 0, omega equal to 0 for the acoustic branch, and omega is some value here, omega naught, for the optical branch. You can easily find out what that is by putting it in the dispersion relationship. So if I set this condition q equal to 0 and omega equal to 0 in this force equation, I get A1 equal to A2, and that means that the displacements are the same. They travel that's like a longitudinal both in the longitudinal mode and the transverse mode, both the atoms get displaced in the same direction. And if I have set q equal to 0 in the optic branch, I get this for the omega naught, and if I put this inside again this expression, I'll get this condition. These are all simple trivial substitutions which I should expect you to do it. That's the reason why I don't want to show it here. I get this condition, and this essentially means that the displacements are opposite. So in the acoustic mode at q equal to 0, I have both the atoms are traveling the same, in the longitudinal case they are displaced in the same direction, but in the optical mode they are displaced in the opposite direction. So this condition, you can easily see that it means that the center of mass remains the same. So you can see that the displacements are opposite, but the center of mass remains the same, remains static, it doesn't move. So this is for longitudinal modes. The same thing I can write for transverse modes as well. For transverse modes, you can see again the displacement is the same. In both of them, they get displaced in the same direction, but perpendicular to the direction of propagation of the wave. And again here the displacements are opposite. The black atom goes up, the white atom goes down, and so on. But if I imagine the atoms and the bases are having opposite charge, then this kind of a mode can support an electromagnetic wave inside the solid. If it's a dielectric, then I have this kind of a lattice wave possible in the presence of an electromagnetic wave. Now that's all I have to say about the harmonic approximation. We'll now move on to anharmonic lattice vibrations. Now the simple harmonic approximation is not enough for accounting for several physical phenomena that we see in solids, particularly in insulators where the effect of electrons, there are no free electrons, so you don't have the data is not clouded by the contribution from the electrons. So for example, there is thermal expansion. Many insulators exhibit thermal expansion that cannot be accounted for in the harmonic approximation. You cannot account for a finite thermal conductivity. That is, if you in the harmonic approximation, thermal conductivity will be infinite, but obviously no material will have infinite thermal conductivity. The thermal conductivity is finite, so there must be a way to limit the thermal conductivity, and that limiting mechanism is not present in the harmonic approximation, as we shall see presently. Also, there has to be a way for the solid to achieve thermal equilibrium. That is, if I say that I am applying a thermal gradient, and if I remove the thermal gradient, the solid should relax back to the original state. Or if I say that I am holding one end of the solid at one temperature T1, that is possible only when there is a mechanism for thermal equilibrium. That means that there must be a mechanism for the solid or for the lattice waves to gain energy from the external medium and to lose energy to the external medium. There must be a heat transfer on both sides, heat or momentum transfer in both the directions. Then only you can have thermal equilibrium possible. Otherwise, it's not possible. If I think of in the case of think of it like ideal gas. How do you achieve ideal thermal equilibrium in the case of an ideal gas? You must have momentum transfer to the gas molecules and from the gas molecules. Only then you can achieve thermal equilibrium. In the harmonic approximation, it is not possible to achieve thermal equilibrium, as we shall again discuss. So you need to go beyond that. Now, we had seen in the video for on cohesive energies and so on, you have a Lennard-Jones potential, or you have a potential which represents the black line here, which is represented by the black line here. You have a strong repulsive component and you have an attractive component which combines to form this kind of a potential. Now, in the harmonic approximation, you basically assume that this asymmetric potential is basically a parabola shown by the dotted line. Now, in the parabola, the average distance between the atoms, it's basically zero. I mean, however, whether you are in the minimum state or an excited state, they vibrate, and they are going to vibrate in such a manner that the average distance between the atoms doesn't change, right? They're going to, the average distance, the distance between the two atoms does not change whether you are in the lowest energy state or in a highest energy state. That means that the ensemble average of the distance between the atoms given by this is constant, is basically zero. It's basically zero, and you don't have any kind of thermal expansion. But whereas if you actually consider the asymmetric potential, if you look at, if you are at a minimum, there is some value of this, if there's some value for x average, and if you are here, it changes, it increases. As you go to higher and higher energy states, the distance between the average distance between the atoms increases. And when do you go to higher and higher energy states? When you increase the temperature. So the ensemble average of the position has to be temperature dependent. That's how that's when you get thermal expansion, right? But in the harmonic approximation, the ensemble average of the position is basically zero, and it doesn't change with temperature. That is the reason why there is no thermal expansion in the harmonic approximation, where the potential goes as x squared, some constant times x squared. But you need to consider an anharmonic term. So this, for example, is the Lennard-Jones potential shown in the blue line, and this is a Taylor expansion of the Lennard-Jones potential, and you get a harmonic approximation like this. And you can see the harmonic approximation is only valid for extremely small displacements. For a slightly larger displacement, it will not represent the true potential curve the system will obey. So you consider additional terms in the Taylor expansion. So given a potential, if you consider higher order terms in the Taylor expansion, you can get the anharmonic potential, a simple representation of the anharmonic potential. And that's one expression is given by this. The leading term is the harmonic term. Then you have a g cube term, the g x cube term, f x power 4 x cube term, x power 4 terms, and etc. and so on. That's how you basically model anharmonicity. So given this potential for the anharmonicity, you can now find the ensemble average of the distance between the two atoms as given by this. And in this expression, if you basically expand the this term here, basically you assume that the anharmonic term is small. It's present, but it is very small. So you basically expand this term in the ensemble average, and you can write it as this, and it's easy for you to show that the integrals will vanish for x squared, because there is an x here. The terms like x squared and x power 4 will not contribute. They'll go to 0. Because you have basically you're integrating over an odd function. So the only function that will contribute, the only term that will contribute to this is basically the gx cube term, and that gx cube term is basically you have to evaluate it using what is known as gamma integrals and so on. But if you evaluate it, you can't evaluate it straightforward. You need to have some kind of a recursion relation to evaluate that. Those are called the gamma functions. and that after you do the evaluation, which you can show that the average distance now depends on temperature. So now you have a mechanism for thermal expansion. So higher the temperature, higher is the average distance. But notice now it depends on G. If G is 0, you cannot have any kind of thermal expansion. G is 0, obviously there is no the leading anharmonic term is gone. F anyway will not contribute because of its symmetry. Now if you take covalent solids where the bonding is very strong, then the harmonic term, the harmonic force constant C is much greater than the anharmonic term force constant G. So there the thermal expansion will be very low. But if you consider metals, then it turns out that C and G terms are comparable in magnitude, so they exhibit much better thermal expansion. Metals expand obviously, and they exhibit much better thermal expansion. There are many polymers or other materials where the anharmonic term is stronger than the harmonic term, and for them the thermal expansion will be much higher. Now coming to thermal conductivity, if I consider the phonons in a lattice as particles, just like the molecules in a gas, I can derive the expression for thermal conductivity in a manner completely identical to the derivation that we did in the case of Drude model for electrons, and the expression will be the same. It's just 1/3 the specific heat into the velocity into the mean free path. Now what is the mean free path that I should put here? That is, the mean free path obviously means there is some scattering mechanism. What is that scattering mechanism that contributes to the mean free path is the question that we need to answer. Now if I consider a process such as this, that is two phonons K1 and K2 combining to give you a third phonon K3, and the energy is getting added up like this, I can and the wave vectors are short, so I can represent it within the first Brillouin zone like this, and the resultant wave vector is also inside the first Brillouin zone. Now this kind of representation means that if I have an arrow pointing towards the zone center, that means those phonons are getting annihilated, and you are creating a new phonon. Of course, you can talk about this in terms of creation and destruction operators like you do in the case of quantum in case of a harmonic oscillator, excuse me, but I don't want to go into that mechanism here. But this is just a way to represent it. Of course, you can also represent it using normal vector addition. That's also fine. So now the problem here is obviously energy is conserved, but the momentum is also conserved, and that's a problem. There is, how can you have a method to get or let me put it this way. So take the case of electrical resistance. Obviously all materials exhibit resistance, but what does that resistance means? It means that the current that is driven by the electric field is not completely reaching the other side, it's getting scattered. So what is the scattering process here? Here you have momentum conservation and energy conservation as well. This momentum is crystal momentum. So the crystal momentum in this case is conserved, and there is no way for you to scatter the phonons in a direction opposite to the heat flow. Unless the phonons are scattered in a direction opposite to the heat flow, that means the momentum is lost. Some momentum is lost in the process of heat conduction. If that does not happen, then there is no way for you to limit the thermal conductivity. The thermal conductivity will, whatever heat you give to one end of the solid will completely pass to the other end of the solid without any kind of resistance. That's obviously doesn't happen in real life. But what is the source of resistance? Obviously, this is called a normal process. A normal process cannot create that source of resistance because momentum is conserved. The other way to look at it is, now suppose I calculate the total phonon wave vector. That is, in the first Brillouin zone, I add for one wave vector k, I find out the average number of phonons that occupy that energy state, that's just given by the Planck function, or basically the Bose-Einstein function with the chemical potential 0. So this product I evaluate over the entire zone boundary for all possible polarizations and so on. Now, we had seen this in the case of block electrons. This is basically an even function because omega s of minus k is basically omega s of k. The frequency is the same for both wave vectors, but you have this k and I'm summing it over the first Brillouin zone. Obviously that sum will be 0 because I have positive k and negative k. That is it's an odd function, or summed over the first Brillouin zone it will be 0. So in the case of when there is no external perturbation, then if I calculate the total phonon wave vector, it will be 0. Now suppose I apply some heat to the solid, I create some thermal gradient or whatever, I establish it. Then I suddenly remove the thermal gradient. So when I establish the thermal gradient, this total phonon wave vector will be non-zero because obviously you are having some heat flow from one end to the other. The higher higher energy for phonons will be more populated than the lower energy phonons. Please excuse me if by mistake I say photon. Sometimes it happens because of because how closely they sound together to each other. So the high frequency phonons would be excited because of the thermal gradient. So there will be an imbalance in the total phonon wave vector. This will no longer be 0. You are basically setting it to some value. I don't know what it is. It's non-zero. Now I suddenly remove the external perturbation, the thermal gradient. Now the system should relax. It should gradually decay to this equilibrium state where it is 0. But the point is, if I only have normal processes where the momentum is conserved, there is absolutely no way for a system which is at some non-equilibrium state to decay back to its equilibrium state. There's no way. And in fact, you can show that if I don't have any kind of mechanism to equilibrate the system, that is, there's no scattering process, there is no way to lose momentum, the thermal conductivity will actually be infinite for this kind of a normal process. So you need some mechanism, some inelastic scattering mechanism where momentum is lost. Crystal momentum is not conserved, not the total momentum. You need a process where the crystal momentum is not conserved, so some momentum is basically lost, and that's a form of inelastic scattering. This situation is completely analogous to the electron case. Now remember we saw this Fermi sphere of electrons at t equal to 0. You can see it's the net velocity is 0 because some have positive velocity, some have negative velocity. There's no net velocity. If you apply an electric field, there is a force, and all the wave vectors get displaced by some small amount. If I remove the force, this displaced Fermi sphere must relax back to the equilibrium state. But so some point A should go to point B, and obviously this has to be an inelastic scattering mechanism. The distance from the origin Ka is different from Kb, so it has to be an inelastic scattering mechanism where there is a loss of momentum. If you have consider elastic scattering, the Fermi sphere will keep increasing. So for example, here if I insist Ka should be equal to Kb, Kb will be here, which is much bigger than the original Fermi sphere. That's not physical. So the same problem is happening here. If I consider only normal processes, only elastic scattering, there is no way for the system to go back to its equilibrium situation, and you can show that it corresponds to infinite thermal conduction. So there must be a mechanism for inelastic scattering in the case of phonons to limit the thermal conductivity. So that process is called the Umklapp process. Umklapp means in German to turn back. So let's consider two wave vectors k1 and k2 combining to form a new k vector k1 plus k2, but that k vector is long and falls outside the first Brillouin zone here. But because of the periodicity of the lattice, the point in whatever point in this just outside the Brillouin zone must be identical in all manner to the point to this corresponding point inside the Brillouin zone. These two points are separated by the reciprocal lattice vector. in this case by a capital vector capital G, excuse me, reciprocal lattice vector capital G. Kittel uses capital G, Ashcroft uses capital K. So I'm sorry, there's a confusion. So there's a so if this K1 plus K2 falls just outside the first Brillouin zone, that point should be exactly identical to the corresponding point inside the first Brillouin zone, and these two points are separated by the reciprocal lattice vector capital G. So I can now think of the resultant K3 as forming here. Now notice, this is a crystal momentum is not conserved here. The resultant K3 is in the opposite direction. K1 and K2 are in this direction. K3 is in this opposite direction, which means there is a loss of momentum. This inelastic scattering process is what is necessary for the system to go back to the equilibrium state when the heat source is removed, or this inelastic scattering process is necessary to ensure that there is always some form of thermal resistance and the thermal conductivity does not become infinite. Just in the case of charge transport, excuse me, in the case of charge transport, you always have some kind of inelastic scattering. That inelastic scattering is the interaction of the electron with the lattice vibrations, or the interaction with the electrons with the defects in the crystal. And similarly, you have inelastic scattering processes here, but these scattering processes are where the phonon wave vector is large and falls outside the Brillouin zone, but because it is completely equivalent to a point inside the Brillouin zone separated by a reciprocal lattice vector, I can draw the effective resultant here. So now if you look at the temperature dependence of the thermal conductivity for a very nice clean crystal, it has a very bizarre form. Now at high temperatures, if you take the form of the thermal conductivity, the specific heat is more or less constant. The density of the phonons, excuse me, this is a mistake, I should say density of phonons, not other, there's no other here, excuse me, I don't know what I was thinking. The density of phonons at high temperatures, if you take the Planck distribution, you can easily show it scales as temperature. At high temperatures, the Planck distribution, basically the number of phonons will increase with temperature. When the number of phonons keep increasing, then that means that the scattering will also increase, and the mean free path will go as 1 by T. So higher the temperature, shorter the mean free path. So you have, this is the situation here, you have excessive scattering and the mean free path is very short, and therefore the mean free path goes as 1 by T and the thermal conductivity falls down as 1 by T. Now this is the region where there is very strong Umklapp scattering. This is the process where there is a lot of inelastic scattering and the thermal conductivity is actually low. Now if you start decreasing the temperature, the Umklapp scattering comes down, because for Umklapp scattering the wave vectors must be longer in length. The resultant wave vectors will be longer in length. That doesn't happen at lower temperatures. Only the Umklapp scattering corresponds to high frequency phonon modes. High frequency phonon modes only participate at high temperatures. If you decrease the temperature, those Umklapp scattering states will freeze out, and therefore the thermal conductivity increases, right? But then you hit a maximum, and that's where you have thermal conductivity with the defects and so on. Now at low temperatures, you have again the specific heat goes as T cubed, which is the Debye law. Basically all the high frequency phonons are frozen out. You have only the low frequency long wavelength phonons participating in the scattering, and because of that, what happens is the mean free path is very large. The mean free path actually becomes equal to the length of the sample, length of the dabba in which the gas in which the solid is, length of the solid, I'm sorry, not the gas, the dimensions of the solid, excuse me, I'm thinking of a gas. The mean free path basically becomes equal to the dimensions of the solid, and it becomes constant. The velocity also is more or less constant because it's long wavelength. It's like sound. You basically have sound velocity. In the Debye approximation, you can think of the sound velocity as approximately constant for all the modes. That's what he did. So V is constant, L is more or less constant, specific heat goes as T cubed, and therefore the thermal conductivity goes as T cubed here. So that's essentially how you explain the temperature dependence of thermal conductivity. You need the Umklapp scattering to lower the thermal conductivity. Otherwise, if there is no Umklapp scattering, this thermal conductivity will keep going up. It will keep zooming up. Only because of Umklapp scattering at high temperatures, when they start kicking in, you get the thermal conductivity to fall down. The thermal conductivity falls down only because of inelastic scattering. At high temperatures, it goes as 1 by T. Because the mean free path goes as 1 by T, because the density of phonons goes as T, and the higher the density of phonons, more the scattering, so mean free path goes as 1 by T. So the essential point is you need this Umklapp scattering as a source of inelastic scattering to produce thermal resistance or to limit the thermal conductivity in a solid.